to get the rules. But when you move those gambling games to real life, like the probability of getting a disease, suddenly that's really different than the probability of getting, the ace of diamonds dealt, right? But the same laws of probability apply when you are doing these random type events. Okay, so probability is the science of chance, right? And so we're going to talk about the idea of probability, how we use it every day in all the time in our everyday lives. The search for randomness. What does random really mean? Does it even really exist? You ask a physicist, they may say, nothing is random, right? Probability models, probability rules, and we're going to look at finite probability models. It's how we model the world and make predictions. Continuous probability models. Okay, there's two main ones we're going to look at, and that is basically looking at the area under the curves. You remember that from chapter 3. So we're going to get that table back from chapter 3, then use it for probability, because it turns out that the area under a curve is equal to the probability, right? So we use that. And random variables. What are random variables? And the personal probability as well. So we'll get started. So the idea of probability and randomness and probability. So chance behavior is basically anything that appears to be unpredictable in the short run, but we know that when we run simulations, and this goes on and on and on, when you run it in the long run, it has a pattern. It's not unpredictable. It's very predictable. For example, flipping a coin. Flipping a coin once, heads, I win, tails, you lose. Just kidding. But heads or tails, you flip a coin, heads or tails, right? It's going to be random. We don't know what it's going to be. It could be, unless you're a physicist and they're looking at the speed and the height and the velocity and all that. But if we take that out and we go, we're just flipping this and we're going to see, is it heads or tails? It's very unpredictable. It could go either way, right? Who's going to win the World Series, the MLB World Series? Is it the Blue Jays? Is it the Dodgers? Is it Seattle? We don't, right? We can do these probabilities. But in the long run, if I continue to flip the coin and do it and keep recording how many times I get heads and how many times I get tails and how many times, it will start to converge and settle down to be, the probability is 50-50. And then it becomes very predictable, right? And if it's a fair coin, we're assuming it's fair. If it's unfair, there might be more weight and it could be biased to one side or the other, right? Sort of like a casino. A casino in the long run, this is how they win. The house always wins. Why? Because of the rules of probability. They have it so that they win 51% of the time and you win 49%. They will always, in the long run, they win. You don't have the long run. You don't have that kind of time. As an individual and one gambler, you don't have that kind of time. But they do, because they're the casino. So in the long run, it always converges to a very predictable amount. And it will be, in this case, 50-50 if it's a fair coin, or if it's not a fair coin, it could be 51-49 or 52-48, right? And the only way to know is if you run the simulation, okay? Or test the coin and make sure it perfectly is fair on each side using physics. You can use physics to go, yes, this is perfect. And they do. They weight these coins. They weight the casinos will weight the dice and make sure it's like perfect, right? In Las Vegas, they do. So that it is fair, but it's designed, everything's designed for the house to win based on all these. So we have if you think of randomness, computers, including applets, right? Computer programs. they can appear, we call them pseudo-random because they are still using an algorithm, a very predictable algorithm. But when you just think in the short term, it's going to be unpredictable. But in the long term, it's very predictable. We can use random number tables. That's sort of becoming old-fashioned, kind of like we don't use that because we have computers. We can randomize. We can get a random number just with our phones. Just get an app, get ChatGPT, somebody, right? We can use those to get random numbers. Physical means actually physically running the simulation, like actually running, flipping the coin or rolling the dice. Chaos theory, that's way beyond the scope of this course, but it's studied to show randomness, and quantum mechanics as well, way beyond the course, but it's just talking about what randomness is and how, just know though, in the long run, it's very predictable. In the short run, it's unpredictable. What we do is we write down all the ways an event can happen. And then we call that the sample space. We denote it in this course and many other courses with a capital S, the sample space. I'll just highlight there, the sample space S. And the sample space has to include all possible outcomes, right? So flipping a coin, there's two outcomes if you only flip it once, heads or tails. But if I flip a coin 3 times, all of a sudden there's, right, heads. I could do heads, 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 tails, 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 heads, tails. There's multiple ways, right? And you write them all out, then you have what's called the sample space. An event is the outcome. And think of these two. We just came from chapter 9, which was experiments. All of these are like experiments. Each time you roll the dice, it's an experiment, right? In a sense, right? So it's the outcome of a random phenomena, and it's the subset. An event is a subset from that sample space. And a probability model, this is when we assign probabilities to those events in the sample space, and it's a mathematical description of a random phenomena. It consists of 2 parts, the sample space S, a way of assigning probabilities to events, right? So sample space S and the way of assigning probabilities to the events. So if I have 2 dice, right? Well, let's say I have 1 dice. Just think of me just having 1 dice. I actually, if you come to my office hours, you'll have seen them. I have dice about this big. You can toss them in the air. So if I have 1 dice and it's fair, how many different possible outcomes are there? What's the sample space? What would it be? Yes. Yeah, so a 6-sided die has 6 sides, and each dot is called a pip. So one side would have 1 pip, 2 pips, 3 pips, 4 pips, 5 pips, 6. So each one. So the problem, if I toss the die into the air and it lands, what's the probability of getting 2? 1 out of 6. So you were going to say 1 out of 6. So it's always the number of ways for that event divided by the total number of all possible events. So it's the number of, that's what probability is. It's the numerator, the number of ways an event can happen, divided by the total number of ways. Number of ways divided by total number of ways. Okay, yeah. And if we extend that to 2 dice, and I like this picture because it's 2 different colors. Again, when you come to my office hours, you can come by. My office hours are Tuesdays, right? And Wednesdays at 11:30, SA 057. You'll see I have 2 different large colored dice because if you notice here, 2 and 1 is different than 1 and 2, right? 2 different events. right here, notice that is different than that. Even though I'm rolling 2, you almost think of it as 2 different points of time almost, like it's just because they're 2 different colors. But a 1 and a 1 is one, right? Just one event. So if I have 2 dice, then I have 36 different ways. So I have 36 different pairs, and each pair they're all equally likely. So the probability of getting a 5 and a 4, a 5 with red and a 4 with white, is 1 out of 36. But the probability of getting a 9, just a 9, the sum of the 2 dice is 9. How many probabilities? What's the probability? How many ways can I get a 9? Pardon? 4. So I can get a 9 by throwing a 5 and a what? Yeah. Yep. And 5 and 4, right? So that's your event. Those 4 ways out of the total possible ways. So it's 4 divided by 36, right? The probability of getting a 9. The sum of the 2 dice at 9. 4 ways. It could be a 6 and a 3, or a 3 and a 6, or a 4 and a 5, or a 5 and a 4. 4 divided by 36. And you can plug that into your calculator, because quite often with our tests, we'll have it as a proportion or a percent. Okay. All right. So you can just make sure you always have a calculator ready. Perfect. Yes. 0.1. So and what you do is you always want to round to like 3 or 4 decimal places, or multiple choice. The answer will be there, but with ours, right? So we have 36 different outcomes, and you can maybe look at questions like, what's the probability of getting a 4 or less? So that would mean getting a 4, right? The sum of the 2 dice is 4, or the sum of the 2 dice is 3, or the sum of the dice is 2. What's the probability of the sum of the 2 dice being 1? 0. Can't happen, right? So the probability there is 0, right? Yeah. What's the probability of the sum of the 2 dice equaling 15? 0, right? 0, right. So anything that's outside is going to be defined of 0. And that brings us to our probability rules. Okay. All right. Probability rule number 1. Probability. So the notation, if you're wondering about this notation, what it means, this is probability right here. This is event A. You could have event X, you could have event Y. A is just, you could have an event star. It's just a variable, like it's just a letter. We could have a smiley face. It's just something that represents the event. So the probability of event A, right, has to be a number between 0, or it can equal 0, and 1. If your probability is 1.2, then it's not a valid probability. So that rule has to be between 0 and 1, all right? So the probability of the sun coming up is 1. So the probability of 1 means it will definitely happen, right? The probability equal to 1 is it will happen, okay? The probability of 0 means just what we just did. It cannot happen, right? The probability of rolling 2 dice and the sum being 1, 0. Probability is 0. So probability of 0 is it will not happen, and probability of 1 is it absolutely will happen. Okay. probability rule number 2. The sum of our S, remember we said S was our sample space, the sum has to be equal to 1. So the sum of all the possible events in our sample space has to sum to 1. If it doesn't, then we do not mathematically have a valid probability distribution. Yes?
Well, 0.5 off from like 100 would be like a 99.5% chance. You can add everything together, so that counts as $1.
No, it still has to be 1. It's a strict rule.
You're 9, it's like rounding error. If it's decimal, it would.
It should still, the sum should still be 1. In this course, you'll see it will still sum to 1. Because it's pretty strict rule that it has to sum to 1 because the complement of that, it brings us to another rule, is the probability of it not happening, right, is 1 minus that event. If there's a residual, like a 0.00001% chance, or 0.00001 probability, then it could happen. It's not 0, right?
Like for instance, like 2 out of 9 is not a perfect benchmark, but you get you a decimal without.
Oh, I see. Yeah. So if you're talking about being like completely accurate mathematically, then you can stay within your fractions. Yes, that's a good point, actually, yes. Yep. But by definition, it is a strict definition where it equals 1. Okay. Yeah. Probability rule number 3. If two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. And we call these two probabilities A and B. They could, remember, they're just letters. They could be X and Y. They're disjoint. We call it disjoint. All right. If they have no outcomes in common and thus cannot occur together. If A and B are disjoint, then the probability of A or B, remember or, if it's or, I always add. If it's and, I multiply, but this is an or. If you see the word or, we don't use the unions and intersections as much in this course. We usually use or and and because it's applied, and then we use a plus for the or. Okay? If you're used to the unions and intersections, this would be the intersection, right? And if you want to see what this looks like, it would be this. You would have A and B. And there's nothing in common. So let's say that you have narrowed it down to 2 cars. You're not going to buy 2 cars. You're going to, though, buy car A, or you're going to buy car B. The probability of buying car A will be, let's say, 40%. And the probability of buying car B is 60%. The sum of the two, right? So it will be the sum of the two. The probability of buying car A or B is going to be 1 in that case. They don't have to add to 1. It's just my example. Okay? But the point is that you're not going to buy both cars, meaning they are disjoint events. There is nothing in common between the two. Okay? And that's the addition rule for disjoint events, also known as mutually exclusive. You may hear it called, it's the same thing, mutually exclusive. Probability rule number 4 is that the probability that an event does not occur is 1 minus the probability that the event does occur. So the probability that an event occurs and the probability that it does not occur will add to 1. So the probability that my flight during reading week is going to be on time then the probability of it not being on time is going to be 1 minus the probability of it being on time, right? So if the probability of my flight being on time is 70%, I hope it's more than that. But let's say the probability that my flight's on time is 70%. The probability that it's not going to be on time is going to be 1 minus 0.7, which is it going to be 30%, right? 0.3. So let's say, so it would be, let's say the probability of A is equal to 0.70, then the probability of not A, that's my flight is not on time, is 1 minus the probability that it is on time, which is equal to 1 minus that, which is equal to 0.3, right? So if the probability of A is 70%, my flight's on time, then the probability of it's not on time is 1 minus the probability that it is on time, which is going to be 1 subtract 0.7, which is equal to 0.3, right? And we can use percents, of course, too, right? But when we do the math, when we carry out the math, we carry it out in proportions, right? And those are our 4 rules, all together there. Probability of A has to be a number between 0 and 1, including 0 and 1, right? They can be any number equal to 0 to equal to 1. The probability of the sample space, so the sum of all possible events has to equal 1. And if 2 events are disjoint or mutually exclusive, they have no outcomes in common, then the probability of A, let's say A and B are disjoint, then the probability of A or B is going to be the probability of A added to the probability of B. That means they have nothing in common. That's our addition rule for disjoint events. And rule number 4, the probability of an event not occurring is the probability of 1 minus the event, the probability of the event occurring. It's the complement rule. We call this the complement rule. Complement. Back here at 9:55, and we'll carry on and keep working through the chapter 12 chapter. Okay, we'll see you in a moment. Okay, we'll get back, just return back to probability rule. I'm just going to show you here with probability rule number 4. We can also say that the probability of A is equal to 1 minus the probability of. So we have the probability of not A is equal to the probability of 1 minus the probability of A. But we can also have the probability of A is equal to 1 minus the probability of. Anyone? Yes? We could have there not A, yeah. So the probability of my flight being on time is equal to 1 minus the probability of it not being on time. And if the probability of it not being on time is 0.3, then 1 minus 0.3 brings me back to probability of A equals 0.7. Right? And so this is equal to 1 subtract 0.3, which equals 0.7. Okay, so you can work it both ways. The complement rule. And if we look at rule number 3 for a moment, we have A and we have B, let's say. Nothing's in common at all. And we have the probability of A or B is the probability of A plus the probability of B. But what would be the probability of A and B? and B. What's the probability? So in words, just in plain language, the probability of event A happening or event B happening is the sum of the two. And then the probability of A and B happening together. Yeah, I mentioned multiply instead, but that is when they're not disjoint. If they're not disjoint and they're independent, we would multiply. But what if they are disjoint? That means nothing in common. They're just like I drew. There's no overlap at all. 0. Exactly. The probability of me purchasing car A and car B, 0, because I already stated I would only, right, would only get one. Okay. So it would be sort of like if we put it in an elementary experiment where we toss a dice. What's the probability, just once, by the way, what's the probability of the pips being 2 or 4? So probability of getting a 2 or a 4. 2 out of 6, right? So what's the probability of it being a 2 and a 4? Can't, right? I can't toss a 2 and a 4 at the same time. It's going to be one or the other. So no, there's no overlap, right? They can't occur together. So that is disjoint event. Rolling a dice and getting a 2 and a 4, 0. Probability is 0. That cannot happen. Okay? Good. Here's an example, rolling 2 dice. So let's say we want to find the probability of rolling 2 die and the sum is 5. So we could get a 1 and a 4. Right? We just did this with 9, right? So it's just the same thing. We could get a 1 and a 4 or a 4 and a 1. We could get a 2 and a 3 or a 3 and a 2. And they're different events, right? Even though it's, so each one is 1 out of 36 plus 1 out of 36 plus 1 out of 36 plus 1 out of 36, which is 4 out of 36, which equals approximately 0.11 or 11%. Right? Do you want to check that? That would be good. Make sure we're good. Yeah. Because these are 4 disjoint outcomes. Right? They're disjoint. You can't get a 1 and a 4 and a 2 and a 3 at the same time. Each event is disjoint, so we add those up and we get 4 out of 4 ways. Remember, it's the number of ways divided by the total number of ways. So 4 ways, and we write, and it's really safe to write these out because it's so easy. You can try doing it in your mind and maybe miss one. So write them out. It takes 2 seconds. You can write it digitally or pen and paper. And then we know the total number of ways is the denominator. So the number of ways divided by the total number of ways, and it gets us to the answer. Rolling, the probability of rolling 2 die and getting the sum of 5. And then what's the probability, though, of not getting a 5? Well, instead of adding up all the other ways, you can just use the complement rule, probability rule number 4, and say the probability that the roll not a sum of 5 is going to be 1 minus the roll a sum of 5. Yeah, so it's going to be 1 subtract 4 out of 36, which is going to be 32, right? Out of 36. And we should get 0.89 for that, approximately 0.89, right? And so we use the complement rule because we're using also rule number 1. Well, rule number 2. Rule number 2 is the sum of all possible events is 1. Well, if the sum is 1, then we take all possible events, the probability of all possible events, which is 1, subtract the probability of getting 5, and that's a 3/6. Make that clear. It's a 3 there. And that gives us 32 out of 36.89, or 89%. Okay. Yeah, so find the easiest way to get to the answer. You can always use that complement rule. It can come in handy sometimes. Okay. Finite. So if finite probability models are used a lot, it's when we can count the different outcomes, and it has a finite sample space. And so we assign probabilities to each outcome, and they must be numbers between 0 and 1, of course, and the sum has to add up to 1, or if they don't, we say it's not a valid probability model. It's not a legitimate probability model. So the probability of any event is the sum of the probabilities of the outcomes making up the event. Okay. So finite probability models, sometimes we call these discrete models, probability models, and statisticians often refer to finite probability models as discrete. I'm a statistician. We usually say, is it discrete or is it continuous? And so we need to know what kind of data we're dealing with, because that makes a big difference in how we analyze it. So this is really interesting. This is Benford's law. And what Benford found is that if you take any naturally occurring list, so naturally occurring meaning like if you have a list of the areas of all the lakes in a certain, in say, Scotland, or the volumes of the lakes, or if you take just any random page in the media even that lists things, or a table of logarithms, or a tax return. This is actually used for tax returns to check if it's legit, if it's been done properly. There's no discrepancies. And what will happen is we don't look at the leading zeros. We look at all the numbers leading with 1 to 9. So we count the number of what Benford did is he counted all the numbers that started with 1, and then all the numbers that started with 2 and 3 and 4, 5, 6, up to 9. And he came up with this distribution, a long run. Remember, the distribution is the long run probability. And he said that the probability of randomly selecting a number from a page of naturally occurring, like let's say even populations, we can all identify that, world populations, countries, 1 will be more common, and it will decrease to 9 being the least common. And so this can be used to see if you have a legitimate record, right? If tax return has been done honestly, because if it's not been done honestly and someone's making up the numbers and changing the numbers, they can use this law and go, no, because this is what it should be. The probability of having 1 is the proportion of numbers that start with 1 should be roughly 30%. And then for 2s, roughly 17.6%, 3 only 12.5%, and it decreases down to 9. So 1 being the most common. So numbers beginning with 1 is more common. If you just randomly took some numbers, it would be the most. And you can look it up. Benford's law, super interesting how this was discovered. Okay. All right. Show that this is a legitimate finite or discrete probability model. How can we show that this is legitimate? We could just add them up, right? Anybody? Yes. Yeah, we can add up all the probabilities, and make sure they all add up to 1. So the probability that the first digit X, and we're using X as the random variable, even though we haven't defined random variable, but X represents the first digit. So the X equals 1, X equals 2, X equals 3, and so forth. So if I do probability of 1, and I add the probability of 2, I'll just use these short forms. Instead of X equals, I'll just put down the number. And 8, 9 is going to equal so 0.301 plus 0.176 plus 0.125 plus 0.097 plus 0.079 plus 0.067 plus 0.058 plus, you can see it's really decreasing here, 0.51 plus 0.046. So it's quite a bit different that the probability of a randomly selected number begins with a 9 versus a 1. It's only 0.046. If we add those all up, and you can convince yourself it all adds up, and I've already checked this several times, it should equal to 1. If they do, and they do, I have some agreements here. If they do add up to 1, we can say that we have a legitimate probability model because it follows the probability, it follows the laws of probability. I think it was probability rule number 2. Find the probability that the first digit for the chosen number is not a 1. So not a 1, we can use the complement rule. Now we could add up, because we know it could be a 2, a 3, a 4, a 5, a 6. We could add all those up. Or we can keep it simple, right? And just do the complement rule. So the probability of not a 1 is equal to 1 minus the probability it is a 1. Because 1 is the sum of all of them. It's taking all of them, the probabilities. And then we just subtract 1. Then we know that it's a quick shortcut to adding all of the probabilities, right? So 1 subtract the probability of 1 will give us our answer, 0.0 or 0.301 is equal to 0.699. So the probability that you randomly select a number from a list, right? And it will be 1 subtract the probability of 1, which is equal to 1 minus 0.301, which is equal to 0.699. Okay, you can just get a sheet of asking prices for real estate. And you'll find it will follow roughly. It won't be exact to Benford's law, but it will follow roughly that distribution. Right? These are the long run probabilities, but if you were to take a random sample, you won't be exact. You will be close though. It will be close. There'll be more numbers on that page. It's kind of neat. There'll be more numbers starting with 1 than 2, 3, or 4. It'll decrease from there. Right? Right. So we call this a finite or discrete. Sometimes we call it just the general probability model. It's just a general model. And we also have the continuous probability model. Well, we're going to see another example of this at the end, where it shows the probability of staying in a hospital, the number of days, after a surgery. So I think that's what I use at the end. Continuous probability model. Now this is not a finite, this is continuous. And what we do is we can, instead of looking for, the probability that X is 5 or looking for specific, we look at ranges when we do continuous probability models. And we look at the distribution. This distribution is not like our bell. This is called a uniform because all the height of that rectangle is all the same. It's constant. So we call it the uniform distribution, meaning all the probabilities between 0 and 1 are equal. So if I say pick a number between 0 and 1, there's an infinite number of numbers between 0 and 1, and they're all equal because you could pick anything just as equal as another number, right? So we call this uniform distribution. So the probability of being between your number, so let's say I say pick a number between 0 and 1, and you pick a number, the probability of your number being between 0 and 0.5, well, the area under the curve is half, because we know that the area of a rectangle is the length times the height. And you can visually see too, right? So it's length times the height. So we would have 0.5. And what's the probability of your number? Let's say you pick a number between 0.8 and 1. The probability of it being between 0.8 and 1 is you want to get the area of that shaded region. So it's good to draw a sketch of these to find, just like we did with the bell. You can do it with the uniform distribution, and we can then find the probability between 0.8 and 1. And it ends up being 1 subtract 0.8. This here, the area is going to be 0.2. Because it's 1 subtract 0.8, that's the length here, and the height of this is 1. How do we know it's a height of 1? We know because the length times the height, the total area has to equal 1. Okay, so the length times the height, that's how we know the height. And so we add those two shaded regions up. So the probability of picking a number less than or equal to 0.5 or greater than 0.8. And in this case, because it's continuous, the equals doesn't matter. We could even remove those little equals. So long as it's inequality, you can have inequality and equals, it doesn't matter. The answer is still the same. Okay? And so that will come out to be 0.5 plus 0.2, which equals 0.7. And if you look at this, you can see that 70% of the rectangle is shaded in, or square, if you will, in this case. And so you might go, well, when is the uniform distribution used? Sometimes you can use it for simple things like the time it takes to get to class or the time it takes to get to campus. Sometimes we'll model these. It will be modeled, let's say there's a stretch of on the 401, there might be a stretch, like a kilometer or a few kilometers along a stretch of a highway, and they will find the probability of an accident occurring in that stretch of highway. And they use a uniform distribution for that to model those sorts of events. So, yeah. All right. And we can also do this with, and again, the practice test and also the textbook gives more examples for practice for this. It's length. You just want to think length times height. Know the height of the uniform distribution and you'll have your answer. And we'll look at more examples when we do our review next week, because we're going to have a review for the midterm as well. Okay. All right, so that's the continuous. Here's another continuous. It's a distribution we know. It's this one, right? Well, why didn't that come out? There we go. It's bumpy. I don't know why it's bumpy there, but we have our normal probability models, and it's the density curve. It's going to be the area under the curve. And that area under the curve, nothing has changed. We're going to find the Z-score. We're going to find the proportion of the area under the curve. Nothing changes. It's the only thing different is that proportion is equal to the probability. Okay, it's really, that's what we use it for. So we'll look at this. So if we look at the heights of women, and let's say they're normally distributed with 64.1 inches and a standard deviation of 3.7 inches, we know how to find the probability of, if we were to, we can get the z-scores of this, but if the question is now, what's the probability of randomly selecting a woman from the population and her having a height between 68 and 70? Well, we know how to find the area under the curve between 2 points. We get our z-scores like this, right? Z-scores, right? We know how to do that. And we do that for both. This is really going weird, my pen. So we find the z-scores. This is the first one, 68 subtract 64.1, divide by the standard deviation, 3.7. And we do it for the 70 as well. And we get those table values, those z-scores, 1.05 and 1.59. We look up the larger number first, and we get that number. So we go here, and we find it here. So the first one was 1.59. So we zoom in, 1.59 is right here. It should be 0.9441. And that's the first number. So that's good. And then we look up the z-score 1.05. And it should match what they have, 1.05, 1.05, which is right here, 0.8531. And that's what we have. You take the different, right? You take the one, subtract the other, and you get 0.091. So the and now that area, which we know how to do from chapter 3, we're using all the tools from chapter 3 and just applying it to answer a question on randomly selecting a woman from the population. What's the probability that her height will be between 68 and 70? We use the same methods, use the same table, and that proportion between those 2 points is equal to the probability, which is going to be roughly 9%. Okay. So it's good. It's useful. That's why when we have data and we plot the data and it looks like a nice bell-shaped curve or a uniform, we're happy. We go, good. We can model this we can model this with known distributions and approximate the probabilities. We can get those probabilities. But if it doesn't look like any distribution we know, then we have to do these complex transformations and so forth. So yes. Oh, that's a good question. So how does the rule, the question is, how does the rule, the sum of all probabilities equals 1? How does it apply to this? How do you think it applies? Well, we have a bell, and the area under this curve, the total area under that shape is equal to 1. That's how it applies. The total area of our curve, our density curve. Same with here. If we have a uniform distribution, we have, usually they look like that, from A to B. I don't know why my pen isn't working very well here. The total area, length times height, total area is equal to 1. That's what makes it a valid probability distribution. So when we're in the continuous framework, the probability of being equal to a specific number, let's say it's between 0 and 1, the probability of randomly selecting the number 0.2, it's going to be 0, because the area under a point, a single point, is 0. But a range, what's the probability of my number being between 0 and 0.5? I can figure that out because I can get the length and the height and get that area.
And I'm not super do that. That would go in time as well as something.
Absolutely, because this is a theoretical, the normal distribution is a theoretical idea. We go from negative infinity to positive infinity. We can imagine it in our minds, but we can't create that, right? But we use the theorems, convergence theorems, and we know that the area, the total area under the curve, we use calculus. I don't know if any of you are taking calculus, but we use integration. And so that curve has a function. And if we integrate the function, it will integrate the total area. That's what integration is, finding the area under the curve. It will integrate to 1. Okay, so mathematically, yes, we can prove. We can prove it. But no real life data is exactly modeled this way. These are all approximations. Heights are not perfectly in this shape, but they're close. And they're close enough for us to get really good approximations for these probabilities. It's the best we have, right? Because this is, aside from having a real crystal ball that we can use to predict future and probabilities, this is, statistics is the best we have to find those uncertainties and probabilities. Okay. Until something else comes along, you never know, right? Yeah. So yeah, so if we repeat the random choice many, many times, the distribution of values of X is the same as the normal distribution that describes the heights, right? So if we put all possible women in the population of interest, then we have the normal distribution and we can find the heights of randomly choosing a young woman from the population and getting her probability. We could also have said, what's the probability that her height is greater than 70 or less than 68 or 72 or right, any number, right? So long as it's a range, it has to be greater than, less than, or between two numbers. It can't be just equal because just equal, the area under a single point is 0. So probability is 0. So that is how the continuous and the discrete distributions are different. And I've been saying a lot, random variable, random variable. So by definition, a random variable is a variable whose value is a numerical outcome of a random phenomena. And the probability distribution of that random variable X tells us what values X can take on. X is this, X is that, and outside those ranges, it would be the probability is 0. And a finite random variable, so if we think of Benford's law, that was a finite random variable. It comes to us on a nice table, and it's usually organized really nice as a table, not an area under the curve that we can sketch. So finite is just a table of values, and it will list the possible outcomes. And you can see the possible outcomes for Benford's law. The probability of the first digit being a 0 is 0. It's not part of the probability model. So same thing, what's the probability of it being 0, well, like a 20? It's 0, right? It has to be a number. So X, the values that the random variable X takes on is 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So this is the finite or discrete model. It comes to us in a table like this, nicely organized. Usually it's a nice probability model. And then the continuous is finding the areas under the curve. Whether it be, in this course, we do the uniform or the normal distribution. If we do the normal distribution, it's just finding the areas under the curves and get our table from chapter 3. right? You will be provided this table for the midterm. You'll have this available and a formula sheet as well. Not to worry. So a finite random variable has a list of finite possible outcomes, usually in a table, and then the random variables that can take on any variable in an interval is going to be our continuous. Convenience, they'll be there for you. All right. Personal probability. What's the probability of passing the midterm? Well, depends on your own intuition, what you've done. Only you know how much you've practiced and so forth. So yeah, we have our own personal probability. So long, it's valid. It's completely valid to have personal probability, so long as it's a number between 0 and 1, right? And they use it in, I think I gave the example business, right? You can use it in business based on your experience, your knowledge. Is a shipment going to come in? What's the probability of what you can give or take, between 30 and 40%. You can use those values in your decision making, right? Yeah, absolutely. That's perfect. Yes, it's subjective. But it can be still very good. It can still be very useful, right? It's very good. And like I said at the beginning of the lecture, when we started this chapter, it's amazing how often we use probability every day, all day in our lives. We are always thinking of chance, right? We're always thinking of it in some way, right? What's the chance of rain? The weather. Is it going to rain? What's the chance? And you start to look outside and you go, is it going to, I don't want it to rain. I want to be outside. I'm going to be at a park or whatever, right? So I'm going out for the day, right? The weather with the probability of rain. So to be legitimate though, it has to be between 0 and 1, and it has to follow those rules 1 to 4. So rule 1 was it has to be a number between 0 and 1. Rule 2, it has to be the sum of all the possible events has to equal 1. The rule 3 is the disjoint events, the probability of A and B. If they're A and B are disjoint, you can say the probability of A or B would be the probability of A plus the probability of B. The probability of A and B is 0, right? If they're disjoint events, that means they cannot happen together. And finally, the fourth probability rule is the complement rule, where the probability of A could equal the probability is equal to 1 subtract the probability of not A. You do the opposite, right? All right. Right, and it's subjective. So the probability of my personal probability of the Jays winning the World Series is going to be different than yours or yours. Like we will all differ. Whereas the probability of flipping a coin and it's fair, it's going to be it won't differ, right? It will be it will be what it is. It is what it is, right? All right, so a couple plans to have 3 children. Let X is going to be the random event of the number of boys they have. Assume that boys and girls are equally likely, although they're not. And we know from empirical data that having a boy or a girl is not equally likely. Does anyone know the probability of having a boy or a girl? Everyone thinks it's 50-50. It's not 50-50. It actually isn't. Does anyone know? And they've done this at all different regions in the world. And if they see an anomaly, like more girls, then they check the water and they check the environment and they see what's going on. But overall, there is a distribution for the probability of boys and girls at different parts in the world. They've looked at this extensively, and it's ongoing because the world is now 8 billion and counting. So they have lots of data. Does anyone know what the probability of a boy? It's approximately 0.48. I can search and we can do a search and get the most recent, but the probability of a boy is 0.52. The probability of a girl is 0.48. So it's higher probability for a boy. There's more boys than girls, males. Yeah. So, and you can check the most recent. I could do a quick search, but we'll keep going with the lecture. I'll check after to see what the census is. It will sometimes change depending on region. Like if you're just looking at Canada versus if you're just looking at this. But if you're looking at the whole world, I believe last time I checked was like roughly 48-52. Always more, boys are always a little bit higher probability than the girls. But for simplicity, let's suppose it's 50-50 and that each child's sex is determined independently. What is the sample space? Right? That's boy. Should I start over? I feel like it's a mess. I know. Let me just see if I can. Let me start over again. Let's get this so we can see it. I'll try to make it as neat as I can here. Boy, boy, boy. And then boy, boy, girl. Okay. Boy, girl, girl. Is that okay? Or should I do a boy there? Boy, girl, boy. Yeah. We can do these two. Girl, 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 boy, girl, boy, boy, girl, boy, girl. Are we good? Any more? So how many ways? 8. 8 ways. And that's just a family of 3. Imagine 5. To keep writing it all out, right? So, yeah. So 2 outcomes, 2 to the exponent 3 will give us the 8 ways. If there was 4 children, it would be 2 to the exponent 4. And you can see it would really exponentially grow. Yeah. Yeah, it would give you 6. But we need this, the sample space needs to be, in this case, has to be 8. No, each one is different because you want to think of the order they're born almost. Nothing. No, it needs to find, usually what we do is we go 2 is the main number because there's 2 ways. Like think of tossing a coin. It's going to be the same thing, right? Or the probability of getting a disease. So, and then the number of ways we're 3. So 2 to the exponent 3. That's how we get to it. Or writing them out. At this point, write them out so you can visually see. Okay, visually see it. It's still really handy. What is the probability? Now, X represents the number of boys. So what's the probability that the number of boys is 2? X equals 2 is going to be equal to, how many do we have here? It has to be exactly 2. So how many ways do we have exactly 2? All right, let's count. So exactly 2 would be this one, and this one, right? So we could have boy, boy, girl, girl, boy, girl, or girl, boy, boy. So that's going to be 3 out of 8. You can leave it like that, or we can get it into a percent. Yeah. or 37.5%. So the probability that this family, and we're assuming, we're simplifying it. It's actually a little more for boys, but if we simplify and say it's 50-50, it's going to be 0.375, 37.5%. What's the probability that the family will have this is more than one boy. So this is greater than one boy. So not equal to one, it has to be 2 boys or 3 boys. So you have to find all those from the sample space. So I'm going to use part A to get to it. And I'm going to go 2 or more. So we have 2 here, and we have 3 here. 2, 2, any more? It's just going to be equal to x greater than 1 is going to be equal to 4 out of 8, which is just going to be, yeah, 50%. Right? 50%. Right? So sex of the baby is considered a random event, and we're assuming independence here. When we say assume independence, that means that any of the events, so just because a family's already had 2 boys doesn't mean that the next one is going to be a girl. Everyone thinks, oh, the girls do, but it's not. It's independent, meaning any event that has happened before will not influence how they're counting, right? With 8 billion of us, we know in the long run, there's a pattern emerging, and that pattern is roughly 0.5152 to 0.4849 for boys and girls. So, all right. Independent events. Here is a finite model, and X can take on 2 days in the hospital after a minor operation, 3 days in the hospital, 4 days in the hospital, 5 days, and 6, but 6 is missing. So before we look at part A, well, actually A is the question. What's the probability that X, now X in this case is now the length of stay. So it's the number of days. X is taking on the random variable, the number of days spent in the hospital after a minor operation. So what is the missing one? What do we do here? How can we find X equals 6? Yes. Perfect. We're going to use the complement rule and the rule number 2 to know that it's which equals 1 minus 0.85. So what is 6? 1.5, right? We usually, oh yeah, you could have, but because we see these as percents, it's nice to do at least 2 decimal places. Yeah. 2 or 3 decimals is nice because then you can see it. Yeah. Yep. Just for, it's for being consistent too. I try to be consistent as I can. So what is the probability, let's say a patient wants to know, what's the probability that a randomly selected person is going to stay in the hospital more than 4 days? So oh my gosh, I can't miss this much work. What's the probability of staying more than 4 days based on the empirical data that we know? If this is the data, then the probability of X being more than 4 is going to be equal to the probability it's X is 5 or 6, right? Which is going to be 0.20 plus 0.15, which is going to be equal to 0.35, right? For more serious situations. I have here the women's heights. I'm bringing it back. It's, except for I'm using Canadian data, I have 163.8 centimeters is the average for the women's heights, and a standard deviation of 6.4 centimeters. It's in centimeters instead of inches, what we had before, but it's done the same. What is the probability that a randomly selected woman, so I randomly select someone from the population, and they are shorter than 172 centimeters? So I just do this, x is less than 172, and x is the height of a woman in this case. We're just saying, it's just way too, we just use it as a short form instead of writing. We could write out the words. What's the probability of the height of the woman being less than 172 centimeters? But x is a nice shortcut, right? It's a nice quick way to write it. And we just do this. We're going to change that x into a z. Why? Because we're going a z-score, so I can get the probability from the table. And I just do this. 172 subtract 163.8, divide by 6.4. And that's going to equal the probability that z is less than 1.28. You can look that up and verify. So what we do is we go to the table and we look for 1.28. It's going to be right here. 0.8997. Everyone see how I do that? This is a kitchen problem, right? It's coming from chapter 3. So that is 1.28 gives us that area under the curve, which is 0.8997 or 89.97%. So the probability that I randomly select a woman from the population, from this population of interest, based on this normal distribution, and her height being shorter than 172 centimeters is quite high. It's almost 90% based on this distribution, based on the average, which is 163.8 centimeters, and the standard deviation 6.4. So we're not just finding the proportion under the curve, we're finding the probability. Okay? And finally, our last question for the slide is, what is the probability that a randomly selected woman from the same data is taller than 172? There's a couple ways we could do this. Yeah. You could just take this number and go one subtract, use the complement rule. That would be the best way, right? If you already know this information, I absolutely would recommend the complement rule, right? Because if this is the probability of her being shorter, what's the probability of being taller? It's going to be 1 minus that. And we know that rule because if we want greater than, we always take the 1 subtract. Now you can see why we do that too, right? Exactly. So the probability, really good question. Let me write that up here as neat as possible. The probability that x equals 172 is equal to 0. Because the area under the curve, 0. Try to use calculus. You can't, right? The calculus will say it's 0. It would integrate to 0. There's no length with a point. So it is, so taller would be greater than. So keyword is taller. That means greater than instead of less than. Here we had less than because that's shorter. Here we have taller than because it's going to be greater than. And so that's just going to be 1 subtract 0.8997, which is going to give me 0.1003 or 10.03%.